Hello class, and thank you for watching section 5.6, rational functions and their graphs. We're going to tackle this in one day, and we're going to go over in this section is how to identify the x-intercepts, the domain, and the isotopes to a rational function. Let's begin by first defining what a rational function is. Now, we have here that a rational function, by definition, is a function where the quotient, it's a function, are the quotient of two polynomial functions, which means that we'll use r for rational. R of x is equal to this polynomial function p divided by this polynomial function q. So in the numerator, we have this polynomial of ax a times a sub x times x to the m power, and we're going to add a bunch of terms until we get to our constant. And then in the denominator, I also have a polynomial in the same format. So it just simply means that we have two polynomial functions that are being divided together. Now, because they're polynomials, they have some of the same characteristics as a normal polynomial, that they're going to have x-intercepts, they're going to have, again, n behaviors and things of that nature. Now, p and q are going to be polynomial functions, and the key thing here, remember, is that the denominator cannot equal to 0, which correlates to the domain of our rational function. The domain of our rational function is going to be the set of all real numbers except for, again, what makes the denominator q of x equals 0. So for whatever x value we get that makes this thing equal to 0, that number gets excluded from the domain. Now, if p and q have no common factors, then the x-intercept of the rational function is the set of all real numbers where the numerator equals 0. Which basically means that if I can figure out what makes the numerator equal to 0, and it is not a value that gets eliminated from the domain, it's a number that's excluded from the domain, then we have an x-intercept at that location. So let's take, for example, number 1 here, 1a. Let's find both the x-intercept and the domain for this rational function. So let's start off with the x-intercept. So to identify the x-intercept, we're simply going to get our numerator, which is x plus 7, and set it equal to 0. When is this going to equal to 0? So just like, again, like in any equation, any polynomial, any function, to find the x-intercept, we're looking and replacing the y value, the output value, as 0, and then solving the equation. This right here requires us to simply subtract 7 from both sides. So x equals negative 7. So this right here would be the x-intercept. Assuming that this number is not excluded from the domain. So let's identify what the domain is now. To identify the domain, we look at the denominator, x minus 5, and figure out what makes that equal to 0. So adding 5 to both sides here means that x will be positive 5. So x minus 5 equals to 0 when x is equal to positive 5. So that means that this number gets excluded from the domain. So that means we can have any value as a graph. That means we can pick any number to the left of 5, any number to the right of 5, with the exception of, again, 5. So we cannot have that number in the domain. So here we're going to write it, at least for this homework, we're going to write, in this assignment, we're going to write it like this, as an inequality. So we're going to say that x cannot equal to 5. So the domain could be anything except for 5, and since the x-intercept that we found here is at negative 7, again, it's not excluded from the domain, because the only number we're excluding is 5, then we have an x-intercept there. That's what I mean, again, with both p and q, the numerator and denominator, have no common factors. So let's move on to the next example. So similarly, we're going to do the same thing to identify what the x-intercept is, we're going to look at the numerator, x minus 6, set it equal to 0. And by adding 6 to both sides, the solution to this equation is positive 6. So this is our x-intercept. Assuming again that this number isn't excluded in the domain. So now let's identify our domain. So for our domain, we're going to get our denominator x plus 7, set that equal to 0, and by subtracting 7 from both sides, we get that the solution is negative 7. So we have to exclude negative 7. So just simply put in a vertical line there saying that x cannot equal to negative 7. This is going to be our domain. So by stating that x cannot equal to negative 7, we're stating that x could be anything else. So x could be positive 6, which is an x-intercept. X could equal to negative 6. X could equal to negative 27. It just can't equal to negative 7. Now moving on to example C, here to identify the x-intercepts. Let's color coordinate this. We're going to get the numerator, set that equal to 0. So x squared minus 81 equals 0. This one, the easiest way to solve this one without having to do factorization is to start the same way as the previous one by adding 81 to both sides. And then we have x squared equals to 81. And now to get rid of the square, we're going to take the square root here. So the inverse operation would be this. So we get that x equals to both a positive and negative 9. Since we're taking the square root, I have to consider both the positive and negative value of the square root of 81, which is 9. So positive and negative 9. Now, again, these would be our x-intercepts, assuming again that these numbers are not a value that gets excluded from the domain. So now let's focus on the domain here. So our domain will be determined by figuring out what numbers are going to be excluded from the real number line. So making the bottom equal to 0, let's see what makes the denominator equal to 0. This one would have to be done by factorization. Since it's a quadratic with this term here, we can move this over here and do the same thing that we did over here by using square roots. This one, because it's a trinomial quadratic, has to be done by factorization. So we have 5x and x. We have a positive and a negative there. And the factors of 54 to give us 3 would be 9 and 6. So x plus 9 equals to 0 means that x will equal to negative 9. So we're going to exclude that number. And x minus 6 equals 0 means that x would have to be positive 6. So that number right there would have to be excluded as well. So our domain here is that x cannot equal to neither the number negative 9, nor can it equal to the number positive 6. And since this number is excluded from the domain, that means that even though we got the solution from this equation, is that this is not an x-intercept. So the only x-intercept that we have here is going to exclude this one, because again, that number gets excluded from the domain. So that means that our only x-intercept is positive 9 here. So let's move on to the next example. So very similar here. Let's start by first identifying what the possible x-intercepts are. So we're going to get our numerator, x squared plus 7x minus 18. Set that equal to 0. And because it's a quadratic trinomial, we'll solve this by factorization. Breaking this apart from x squared to x and x, plus and negative. And the factors of 18 to give me 7 will be 9 and 2. So that means that x plus 9 equals to 0. Means that x will end up equaling to negative 9. And x minus 2 equals 0 has a solution of positive 2. So now let's see again if any of those two numbers get omitted from the domain. So now we get our denominator, x squared minus 5x plus 6 set that equal to 0. Minus, and let's see the factors of 6 to give us 5. That would be 3 and 2. So x minus 3 equals to 0, has a solution of 3, and x minus 2 equals 0, has a solution of 2. So your domain is going to be all real numbers except for positive 3 and positive 2. So those two numbers get omitted from the domain, which means here, when we go back over here, means that this number is not an x-intercept. Something else is going on there. And the only x-intercept we have is at negative 9. Now, if you graph these things, the graph can be a little misleading. So normally, when we look for x-intercept, we're looking again at where the graph is going to cross the x-axis. And in this situation, it's going to be very misleading that when you graph this situation, graph this rational function, that it'll look like the graph is crossing the x-axis at negative 9 and at positive 2. But when you evaluate and plug in the number 2 into the numerator and the denominator, this entire thing is not going to end up equaling to 0. You do get this entire thing equaling to 0 when you plug in negative 9 into all of the x's. This will equal to 0. So if you type in f of x is equal to this function here and evaluate f of negative 9, you will get that the answer is 0. But that is not going to happen when you evaluate it at positive 2. You'll get an error on your calculator and see that you get something that is undefined because something else is going on at that location. Even though the graph, like I said, is misleading, even though the graph looks like it's crossing the x-axis at positive 2. So as you see in this example here, again, like I mentioned, we have f of x equals x squared plus 7x. That's the last example that we did. And you will see again that we do cross the x-axis at negative 9. But when we make the top equation equal to 0, it said that it should be crossing the x-axis at positive 2, and it doesn't cross the x-axis at positive 2. The other thing, again, that's interesting about that is that when I evaluate this function at positive 2, notice that the function is undefined. That, again, has to do that this positive 2 also makes the bottom value equal to 0, which, again, is a big no-no with these rational functions. We cannot have the denominator equal to 0. So this number is not part of the domain. This is not a number that's allowed to be used for a substitution into the values of x. So we can plug in any number for x and get an output value except for the number 2 and, of course, the number positive 3, the positive 3 that we got earlier, okay? So even though it looks like at positive 2 is not necessarily at x-intercept, it looks like it should have an output value. It doesn't. And the same thing at positive 3. Something else is going on at positive 3 that, again, the function is undefined. So just be aware of that if you're going to rely on these graphs to find the x-intercept, that you're paying very close attention that in the case that it actually crosses the x-axis at that location, verify that if I plug it in, it actually does in fact make the function equal to 0, and it doesn't give you something that's undefined. Here clearly we can see that it doesn't cross the x-axis at positive 2, so we don't have to worry about positive 2 being an x-intercept. We are only crossing the x-axis at. So let's continue with the second page on these notes. And in this section, we're going to start first talk about arrow notation and what these arrows mean when in terms of vertical asymptotes. Just so you could see again in the terms of the explanation. We're not going to use them in the answers, just in terms of the explanation. So the arrow notation indicates again as x approaches. So to have an arrow means this term here approaching something, okay? So x arrow to the right of A means x is approaching A. And a positive sign up there means that we're approaching this letter A from the right side. X approaching a from with a negative means we're approaching it from the left side, from the negative side of that value. And then we have again the notation for infinity. So x approaching positive infinity and x is approaching negative infinity, which is another way of saying that x is going to increase without bound, that we're just going to randomly start picking numbers for x to get bigger and bigger and bigger, or decrease without bound, having x to be again as small as possible. Now, like I said, we're only going to use that notation again just to explain the examples that we have here in the definitions. Now, let's talk about vertical isotopes. A vertical isotope is this imaginary line that acts like a boundary that separates the graph into two disjointed, discontinuous parts. And the vertical line x equals to a, so this vertical line x equals a, I'll highlight them in the diagram. These here, these things right here are again called vertical isotopes. And like I said, they create this discontinuity. They create this infinite discontinuity where the graph of f is going to increase or decrease without bound as it gets closer and closer to this position of a, to this imaginary vertical line, as illustrated right here in this diagram. So here, this is our function right here in blue, and notice that from the right side, so from the positive side, as x is approaching this vertical line from the positive side, the y values, f of x, is increasing and is just simply going to move vertical all the way to positive infinity. And the same thing is happening here. The only difference is that on this one, we're approaching again this vertical line. The x values that we're plugging in for the function are numbers less than this vertical number there, but it's doing the exact same thing. So right here, let's say let's say that this number is 5. So if we're approaching again 5 from the positive side, I'm picking numbers bigger than 5, so 5.001, then 5.0001, just getting closer and closer to it until we get as close as possible. Again, this right here would be even closer to this value of 5 from the right side. If we're approaching again the same vertical line 5 from the left side, then it will be 4.9, and as we get closer, as we approach even closer, that will be 4.99, and then 999 after that, until again we get as close as possible. But the output value, which is again the important part here, is again increasing without bound. Now we could have it do the opposite thing. Instead of going upwards, it could go downwards, like the diagram is illustrated right here. Okay, the notation for x is the same. The only difference is that the y values are now going to decrease without bound. So your y values are just getting smaller and smaller and smaller. So as long as the graph is behaving like that, behaving again like this, around this vertical line, around some vertical line there, we call this vertical line a, x equals a, your vertical isotope. So for example 2, let's determine the location of the vertical isotope by the behavior of the graph. So we want to look again is see where the graph has this behavior. It's approaching this vertical line, and the graph is either going up to positive infinity without bound or down to negative infinity without bound, whether it's from the left or the right side of that vertical line. Like in example 2a, hopefully you can see that this end and this end are decreasing and increasing without bound respectively. So that means that there is a vertical isotope. There's this imaginary vertical line here that is causing this discontinuity, that's breaking the graph into two different parts, not connected parts. And the vertical line, since it's intersecting the x-axis at -3, is the vertical line x equals -3. And since it's also doing it's behaving the exact same way on this end, on this side here, Notice yet again that this end is pointing downwards. This is again upwards. It seems like there's another vertical isotope right here at this location, which is again, since it's intersecting the x-axis at positive 3, which is at positive 3. So we have another vertical isotope at x equals positive 3. So this graph does in fact have two vertical isotopes, one at negative and at positive 3. So let's look at example 2b here. So let's do the second example. So again, to identify the location of this vertical isotope, we have to look again at the behavior of the graph, first of all, where the break is, and where exactly we see that the graph is becoming vertical. So we can clearly see that there's a break in the graph in this area right here. This part here is moving upwards. This part over here is moving downwards. So my function f of x is approaching negative infinity as x is approaching some value of a from the positive side. And over here, f of x is approaching positive infinity as x is approaching, again, that same number, just simply from the left side, from the negative side. So it's figuring out what that value is. Well, it obviously can't be at -2 because at -2, the graph is connected there. It can't be -4 because the graph is connected right there. So the jump and the discontinuity is occurring right in the middle between those two values, between -2 and -4. Sorry, let me go back over here, which is exactly at positive 3. Now, obviously, the answers are not always going to be positive 3. The two examples I have here on our notes, just coincidentally enough, are 3. But that's exactly where the graph, again, is behaving, and it's unbounded. It's discontinuous because the two ends are pointing either to positive infinity or to negative infinity. And again, it doesn't matter which direction is pointing where. As long, again, it's becoming vertical, we're going to see that the discontinuity occurs there. So this thing has a vertical isotope at x equals positive 3. Now, of course, the fastest, most convenient way to identify the vertical isotope is if we're actually given a function. Given what is the function rule to this thing, and when given that, we can identify the vertical isotope, as we'll see in the next example. So like I mentioned, now let's look at how we identify these vertical isotopes given the function without using, again, a graph or some type of graphing utility. So if f of x is equal to a rational function, again, p over q, in which p and q, again, have no common factor, that's going to be key here. Q of a, so the value that we plug in that makes the bottom equal to 0, that number that we plug in that makes the bottom equal to 0, a is going to be a vertical isotope. So in other words, all I have to do is figure out what makes the bottom equal to 0. And at any x value that makes the denominator equal to 0, that's going to be the location of your vertical isotope. But the key thing here is that it cannot have a common factor with the numerator. So very similar to the way we identify the domain and figure out what numbers get excluded from the domain of the function, those numbers that we cannot use for x, those are going to be the locations where some of our vertical isotopes are going to be located. I wouldn't say all, because it's not the case, because again, they have no common, the numerator and denominator cannot have a common factor. But this is the reason why these numbers get excluded, at least graphically, why these numbers get excluded from the domain, because in some of these places that make the denominator equal to 0, the bottom part of the fraction, the x values that make the bottom part of the fraction equal to 0, there exists, again, these vertical isotopes. So let's look at some examples of how we identify the vertical isotopes, again, assuming that they have no common factors. So in this first example here, there is no common factor with the numerator because the numerator is just x and the denominator is x minus 9. So to find the vertical isotope, we're simply going to get our x minus 9, our denominator, and set that equal to 0. So this one just simply requires us to add 9 to both sides, and we are done. There. x equals to 9 is the location of our vertical isotope. So here's our function f of x, and just to again show you, since we just talked about how it looks like a graph, we should see again if I make the denominator x minus 9, set that equal to 0, it's going to draw a vertical line, and I see again that that vertical line is that place of discontinuity. Notice how the left end of the graph, as x is approaching 9, the function values from the left side, so 8.9, they're getting bigger. So every time I make it and get closer and closer and closer to 9, my y values are getting smaller and smaller and smaller. You see? More negative, more negative. Now if I approach that 9 from the right side, 9.9 doesn't work, 9.01. Notice I have 901. I get a little bit closer. I have 9,001, get a little closer to 9, 90,001, and even closer, 900,001. So you see it's becoming more and more positive because that's what it's doing again on this end, on the right side of the graph. Notice that that purple graph is just increasing without bound. So this is your vertical isotope. And as you saw, that's just simply the solution to x minus 9 is equal to 0, which is again positive 9. So it's not again a point, it's the line. The line is the vertical isotope, not the coordinates. 9, 0 is not the vertical isotope. It's the line that goes through that point. That is the vertical isotope. So let's continue with the next example. So here's the same thing. To find the location of the vertical isotope, first check that the numerator and the denominator have no common factors. 5 is not the same as x minus 5 nor x plus 5, so no common factors. So all we're going to do is get x minus 7 times x plus 5 and set it equal to 0, which, because it's already in factored form, means that each individual factor can now be set equal to 0, and we have our solutions. So the first solution would have to be a positive 7, and our second solution would have to be negative 5. So there is the location of our vertical isotopes at 7 and at negative 5. Well, let me put them in order. Negative 5 would be first from left to right, and positive 7 would be second. Let's move on to example C. Now in example C, there is a common factor. Here, even though it's not in parentheses, x plus 6 is grouped together. Notice that we have a x plus 6 in the numerator and an x plus 6 in the denominator. So very similar to like reducing the fraction 3 or 3 over 6, which reduces to 1/2, because you could divide both of these numbers by 3. You're going to do the exact same thing with this fraction here. Because they have a common factor, you can factor out this common factor of x plus 6, and you're going to end up with 1, because technically there's an invisible 1 right there. And you reduce the common factor out, leaving only the value of 1 and x minus 8 in the denominator. So in order to identify these vertical isotopes, like I mentioned, there cannot be a common factor with the numerator and denominator. If there is, like in this example here, we want to reduce this out so we can have a simpler form of our rational function. And then with our simpler form of our rational function, we can now focus on the denominator of that simpler form and figure out the solution of what would make, in this case, 8 minus x minus 8 equal 0, which would simply be positive 8. So here we only have one vertical isotope at the location of x equals 8. And if I was to graph this, I would see exactly that. Something else is going on at the x plus 6. Okay, whether it looks like it's crossing the x-axis at negative 6 or something else is happening at x equals to negative 6, but the one thing that is not happening is the vertical isotope. There's not a vertical isotope there. So here is exactly what I'm talking about. So here I have the graph function, and notice that there's only one vertical isotope. So even though I get x minus 6 and x minus 8 equal to 0, which is going to draw two vertical lines there. Let me change the color of this. You'll notice that both of the vertical lines are not isotopes. Notice that in this vertical line here, the graph actually intersects again at that value. So it looks like it will be defined at that location, but it's not. We only have the one vertical isotope at this location of x minus 8. We can clearly see the discontinuity there. Something else is going on at this location. For those of y'all that have studied again pre-calculus or have taken AP pre-cal before this course, you should recall that there's holes. There's situations where rational functions have holes. So while it's not something that you'll need to know for this course, you can again rely on that prior knowledge if you recall, and you'll see that we have a hole in that location. Because when I evaluate my function at 6, notice that yet again it's undefined. So it's a little misleading again that it looks like it's continuous and it's connected right here at 6. But when I plug in 6, I see that I don't have an output value. It's undefined. So there's no output result of that. This is the reason why this 6 is not part of the domain. So just because a number gets excluded from the domain doesn't automatically mean that we have a vertical isotope in that location like I mentioned earlier. So be very, very careful in those situations and verify that there is no common factor in the numerator and the denominator. So when I factor this out and I come up with a simpler form of f, let me call it g, which was 1 over x minus 8, you'll notice that the two graphs look exactly the same. This blue one here, the blue one there, and that red one right there. You see, they look exactly the same because I've simplified and I factored out the common factor. So continue with the next example, similar situation here. Since these things are already in factored form, we can factor out the common factor. The x plus 7 is a common factor. We can divide that out, which is going to give us a simpler form of this. It's going to be x plus 8 over 1, since this is technically 1 times x plus 7. And x plus 8 divided by 1 is just x plus 8. Now notice that there's no denominator here, so there's nothing to make equal to 0. We cannot have in this format here, 1 cannot equal to 0. So this one has no vertical isotope as a result. The only vertical isotope that would result we had a denominator with a value of x times or plus some constant that we can solve an equation for. But in this case, since there isn't, there is no vertical isotope. Now for the last two examples, we don't have the polynomial in the numerator or in the denominator in its factored form. So we are going to have to factor it before we identify what the vertical isotopes, because again, we have to make sure that there is nothing in common in the numerator nor in the denominator. So let's split the bottom part. X plus 6 is easy, it's already, again, x plus 6, so nothing to do there. But we can factor the quadratic trinomial into, well, plus and plus. X squared is x and x, plus and plus there. The factors of 12 that are going to give me the value of 8, 1 and 12, 2 and 6, 3 and 4, so 2 and 6. So 2 and 6 multiplied to give us 12, that add up to 8. So splitting up that trinomial we have there. And there you have it. Look, factors of x plus 6. So simplifying this, we end up with 1 in the numerator, x plus 2 in the denominator, which means that the vertical isotope is only going to be the result of finding what makes x plus 2 equal to 0, which the answer to that is negative 2. So this is the vertical isotope that this graph will have. So here similarly, before we identify what makes the denominator equal to 0, let's make sure that there's no common factor with the numerator. And we can factor both the numerator and the denominator. The denominator is a difference of squares, so that's just simply going to be x plus, x minus, where we simply take the square root of both the x and the 9, which is going to be 3. X, 3, and 3 right there. Now to factor the quadratic trinomial on top, we're going to separate the x squared to x and x. This sign is negative, so that makes that negative. And so negative times a positive is negative. Then the second factor is also going to be negative. So we're looking for factors of 15 that give us 8. So that would have to be 5 and 3. Now, we see that there's a common factor of x minus 3. So we factor those out. We simplify this this rational function to x minus 5 over x plus 3. So that means that the only vertical isotope here would be the solution of x plus 3 equals 0, where the solution is negative 3. So if you graph this, okay, and you draw the line x equals negative 3, you'll see that this is going to be a vertical isotope. But if you were to graph this and make this graph the x plus 3, x minus 3 like I did before, make that equal to 0, you'll have two vertical lines, but on one of them, the graph is not going to behave again, like I mentioned. It's not going to be approaching infinity nor negative infinity from one of the two ends or from either end. So again, when you're going to look at the graph, make sure again you understand the behavior that the graph the behavior of the graph as it's approaching again these vertical isotopes. And now finally, let's discuss the last thing in today's lesson, which is horizontal isotopes. The line y equals b, which is going to be a horizontal line, is a horizontal isotope of the graph of the function if f of x approaches this line as x increases or decreases without bound. Even though it could happen on both ends, even though it does happen on both ends, not if it happens, but since it happens on both ends, we're only going to be focusing on as x is approaching again, increasing without bound. So in other words, as x is getting closer and closer to infinity, all right? Now, because of this, since we're looking at the values of x again without bound, increasing to positive infinity, that means that the horizontal isotope of a rational function describes its end behavior. It's going to tell us again how the graph is leveling off and how it's going to become horizontal. Now, one key significant difference between a vertical and horizontal isotope is that our vertical isotopes act like boundaries, like magnets, where the graph is not going to connect, is not going to cross any vertical isotope. But horizontal isotopes are the complete opposite. We can have functions that are always below or always above the horizontal isotope, but then we can also have functions that actually intersect the horizontal isotope at some point, but then eventually again, as x is becoming extremely large, it's going to level off and just get closer and closer to this horizontal line. So here in this diagram, our horizontal isotopes are these horizontal lines I'm highlighted in yellow. So the way we find them again is that we're basically looking just at the end behavior. So we look at the very far right, or even in some cases on the very far left, wherever this graph is leveling off, its end behavior, that's going to be the location of the vertical isotope. So take, for example, this one right here. To identify the location of the vertical isotope given a graph, we want to look again at the end behavior of this thing. So we want to look at the very far left and see where this thing is leveling off. So we look at the very far right. We see that it's leveling off along the y-axis. It's become more horizontal as approaching the y-axis. I'm sorry, that's not your y-axis. This is your x-axis, which is the equation y equals 0. So this is the location of your horizontal isotope. The horizontal line y is equal to 0. You can also find that if you look at the other end at the very far left, getting my left and right confused here, at the very far left, and see that this end again is approaching again this horizontal line, which again is your x-axis, or notably the equation y equals 0. Now, I hope you noticed on the previous example, let me go back to it real quick, that here we see that the middle portion of the graph actually intersects again the horizontal isotope right there in the middle, which it can. This will never occur with vertical isotopes. Vertical isotopes, again, are a lot stronger, and they, again, make the graph discontinuous. So they act like a very strong magnet that doesn't allow the left and right end of the graphs to attach to each other and are separated again by the isotope. But with horizontal isotopes, we can have situations where pieces of the graph or something in between the graph, in between again the end behaviors, can actually intersect the horizontal isotope. That's not always the case, like you see in example B. We go back to this one. This one again is separated by the horizontal isotope, and the two ends again are not, the graphs do not intersect the horizontal isotope. And we can see that the horizontal isotope is this horizontal line, which is intersecting through the y value of 2. So y equals 2 is our horizontal isotope. So moving on to the next example here, to identify the horizontal isotope, I'm simply going to focus on either again the left or right end. So if I look at the right end, I see that this end is becoming more horizontal as we get closer to this horizontal line, which is at the y value of -1. So that is your horizontal isotope. Now again, the horizontal isotope describes the end behaviors, not just the positive end behavior, but the left end behavior as well, the negative end behavior. So as x is approaching negative infinity, you could look at that other end and see where the graph is becoming horizontal. So if one end isn't very convenient to use because you can't tell where it's leveling off, then use the other end, and you should see that that end is also going to level off at the same horizontal line. In this case, of y equals -1. And I want to finish with the last example here of a situation there is no horizontal isotope. Like I see right here, the behavior again of the graph, it has to level off. So the definition of horizontal isotope means that as x is approaching again infinity or negative infinity, the y values have to again approach some value of b. Has to again approach some number. Notice that this end is not approaching one value. It's becoming smaller and smaller. It's going to approach -6, but then it's going to continue moving down and approach -7, and it's going to continue moving down and get to -8, -9, and so on and so on. So you see, it's not getting closer and closer to a constant, to a horizontal value. So this one has no horizontal isotope at all, because the end behavior is not leveling off. So in order for a rational function to have a horizontal isotope, again, the end behavior has to level off. It has to be bounded by some horizontal line. This end right here is not bounded. It's going to keep on decreasing, and as a result means that there is no horizontal isotope. And if you look at the other side, same thing over here. This end right here is unbounded as well. It's approaching 8, but then because it's going to continue moving onward, it's eventually going to reach 9, and then reach 10, reach 11, reach 12, and so on and so on. So there is no horizontal boundary. Again, no bound at all, no boundary in order for it to become horizontal. So again, no horizontal isotope. Okay, so let's now talk about how do we do this when we're given the rational function. So instead of doing any type of actual math, we're going to look at conditions and focus on the leading term of both the numerator and denominator of our rational function. Remember, our rational function is made out of a polynomial function divided by another polynomial function. So that means that there's going to be leading coefficients. So if I focus on the leading coefficient in the numerator and the leading coefficient in the denominator and focus on the individual degrees, focus on this number there, focus on, let me highlight it, this number right there and that number right there, I can determine the location of the horizontal isotope by one of the three conditions. The first condition has to do with the graph that we did on the previous page. This one right here. When is the horizontal isotope going to be 0? The horizontal isotope is going to be 0 whenever this exponent up here, the degree of the numerator, is smaller than the degree of the denominator. So if we see that the exponent up and the top is smaller than the degree on the bottom, that exponent m there, then your horizontal isotope is always going to be 0. For example, 5a and b. Notice at the degree of the numerator, we have 4x to the first power divided by 2x to the second power. Since 1, and again, I don't care about everything else, I'm only focusing on the leading coefficient. Since the degree of the numerator is 1, while the degree of the denominator is 2, 1 is smaller than 2, then the horizontal isotope is going to be 0 every single time. Doesn't matter what any other values are, your answer is always that in terms of the horizontal isotope. Similarly, in example B, since the leading term in the numerator is 9x to the second power and the degree of the bottom is x to the third power, again, nothing else matters but those two exponents. Since 2 is smaller than 3, that means that the horizontal isotope again is going to be on the x-axis. Y equals 0. The second case is if those numbers, those degrees on the leading coefficient are the same. Case number 2. If they're both equal to each other, the degree of the numerator is equal to the degree of the denominator, then the horizontal isotope is going to be the ratio of these two values, which means all I have to do is just divide those two leading coefficients. Take, for example, 5c and d. Here, the leading term of the numerator is 4x to the second power, and the leading term of the denominator is 2x to the second. Again, the degrees are both 2. 2 is equal to 2. 2 equals to 2. So that means that the horizontal isotope is going to be the ratio of these leading coefficients. So 4 divided by 2, which simply reduces to 2. So your horizontal isotope here is the horizontal line y equals 2. Similarly, for example D, same thing. We have 9x to the third power, that's the leading term on the numerator, divided by x to the third power, again the leading term in the denominator. Both again, how do I know they're the leading terms? Because those are the terms with the highest degrees. Okay? And since the degrees of both are the same, they're both 3, then that means that the horizontal isotope is simply going to get the ratio of those leading coefficients. So 9 over 1, which is just 9. So your horizontal isotope is y is equal to 9. So this happens in terms of graphs. This happens when the graph has been shifted upwards or downwards. So like an example B here, in this example here, notice that the horizontal is y is equal to 2. That means that the ratio of ax to the m power divided by bx to the n power, that's going to end up equaling to 2. So that means that these degrees are the same. So this is like to the second, or third, fourth, whatever. And these two numbers are going to simplify to 2. So 2 over 1, 4 over 2, 6 over 3. All right, it's going to happen something like that. And the same thing like over here. Here, because the horizontal isotope was at -1, that means that the polynomial on the top, ax to the power of m plus everything else, divided by the polynomial on the denominator, bx to the power of n, that means that both of these numbers were the same. Whether that number again is 3, 4, 6, 8, doesn't matter. We know that they're going to be the same. And more importantly, is that the ratio of these two values are going to divide and give us a value of -1. So it could have been +1 and a -1 down there, or vice versa, or a +2 and a -2, or whatever the case is. But when I divide both of those two things, those are going to equal to this ratio of -1 as a result. And then lastly, this takes us to our last condition. is the opposite of the first condition, that the degree in the numerator is now actually bigger than the degree of the denominator. So we want this number up here to be bigger than that number there. In that situation, there are no horizontal isotope. That's similar to the diagram that we had in the previous page, this one right here, where we had no horizontal isotope. So if I graph anything that has that kind of condition, I would see that the ends, the left end and the right end, are not going to level off, that they'll be either going to positive or negative infinity on one end, and maybe the same or in the opposite direction on the other end, but they're not going to be horizontal, and they're not going to be approaching against some constant value of b. So take, for example, 5e and f. If we just again focus on the leading term, the term with the highest degree, 4x to the third power and 2x to the second, since 3 is bigger than 2, then no horizontal isotope. And the same thing with example f here, okay? 9x to the second power divided by 3x to the first, since 2 is bigger than 3, again, no horizontal isotope. So that concludes the notes for section 5.6. Hopefully you found this video helpful. If not, again, please message me through email. And if you have any trouble with the homework, or through Parent Square also, but if you have any trouble with the homework, again, check out the videos associated with the individual homework problem, or you could also just click on message the instructor and send me a message through that way. Like always, I appreciate you watching, and I hope you have a great day. Goodbye.